2, Physics 272. And if this is the class you thought it was going to be, then that's good. And if you meant to go to another class, stick around because this one is going to be cool. You're going to learn some nice stuff. Today, we will look at how strong are electric forces. So we'll try to get an intuition for that. Just how strong are these guys? We'll also discuss the electric field of a charged sphere and of an electric dipole. Now, last time we went over what's the electric field of a point charge. Okay? So the electric field of a point charge, we said, had some constants out in front. It depended on the total charge of the point charge. It fell off like 1 over r squared, and it pointed away from a positive charge. So remember that? It kind of looked like a dandelion, and it pointed away from a positive charge and pointed towards a negative charge. We're going to use that then to build up what's the electric field of other objects. So we'll use that today. And we will discuss the superposition principle, which is basically this, that the total electric field at any point in space is the sum from all the charges that are exerting electric fields. That's what we'll do today. But first, the ultimate smackdown, gravity versus electricity. Who would win in a fight? Vote with your eye clickers. It's just a vote, but I will give you credit for having voted. So go ahead and vote. Who would win in a fight? Battle of the forces, gravity versus electricity. Would you like me to open the clicker question? Yes. Okay. Voting is opening. Wow, the votes are rolling in. 140 votes so far. And they're still piling in. Still piling in. All right. Excellent. All right. Overwhelmingly, the votes are that the winner will be electricity by, let's see, 87% of people are choosing electricity as the winner. Well, all right. It doesn't matter which way you voted. That was just for fun. And I'm just going to leave that open in case you want to keep voting. Why not? So we actually are going to attempt to answer this question scientifically. Okay? We're going to apply actual math and logic to answer the question, who will win in a fight, gravity or electricity? So let's do some calculations. We need a fair fight, though, okay? We gotta set up some rules. So here's going to be the rules of the fight. I'm going to do this in a hydrogen atom, all right? So a hydrogen atom is made up of 1 proton and 1 electron, okay? And I'll simply assume that I have a proton and an electron with a particular distance between them. We'll calculate the gravitational force between them and the electrical force between them. First up is the gravitational force. Now, this is a cartoon of a hydrogen atom. It's not a real photograph. I hope you know that. So we always draw these cartoons because it's very difficult to draw the real thing. In reality, what the electron looks like around the proton in the hydrogen atom is it's very fuzzy. Okay, so you know from chemistry, this isn't really it, right? If I put it in a 1s orbital, a 1s orbital is actually a spherical wave around the proton, and it's got spherical symmetry. Think of it like kind of a fuzzy ball, okay, like a fuzzy ball. And so the electron is zooming around, but on average, it's basically covering everywhere, but mostly hanging out close to the proton. And in fact, it's zooming around so fast that if you tried to touch it, it would, you know, you'd feel it, right? You'd feel it everywhere. It's kind of like when you turn a fan on, right, and the fan blades start whirling around. You do not want to put your finger in there. It's almost like it, you know, it's filling all space just by virtue of moving fast. So the electron's filling all this area just by moving fast. It does have an average distance. The average distance between the electron and the proton in a hydrogen atom is the Bohr radius. So we'll just say, for purposes of making this a clean fight, r equals 5.3 times 10 to the minus 11 meters. The rest of what we need is, here's the force of gravity between those two objects, between the electron and the proton. There's a gravitational constant out in front times m1, m2 over r squared times r hat. R hat just gives you the direction. We just want to know a magnitude, so I'm going to not worry about r hat, just the magnitude. So, and here's the mass of the electron and the mass of the proton. If we're calculating the gravitational force, that's what we need. So the mass of the electron is pretty small, okay, kind of a lightweight, 9 times 10 to the minus 31 kilograms. The mass of the proton is 1.7 times 10 to the minus 27 kilograms, and we'll use that in our equation. But notice how different these are in orders of magnitude, okay? A proton is about 10,000 times heavier than an electron, okay? So that's worth kind of keeping in your head. The fact that the proton is so much heavier than the electron, that's why when we think about hydrogen atoms, we just pretend that the proton is sitting still. Really, they're both kind of swarming around each other, and the proton moves a little bit, but it moves so much less than the electron that we pretend it's just sitting still. So the mass of the proton is huge compared to the mass of the electron. Now we put all of that in, and we just want to know what's the gravitational force between these. So put the constants in. The constant of gravity is 6.7 times 10 to the minus 11 Newton meters squared per kilogram squared. The mass of the proton goes here, 1.7 times 10 to the minus 27 kilograms. The mass of the electron goes here, 9 times 10 to the minus 31 kilograms. The distance squared, right? In the equation for the force of gravity, we need 1 over r squared. Our r is 5.3 times 10 to the minus 11 meters. Now I square the whole thing. Now, I'm just interested in who's going to win, right? Who's going to win this fight? Gravity versus electricity. So I just want the order of magnitude of this force. That's what this over here means. I have a squiggly equal sign equals O of 10 to the minus 46 newtons. What I'm interested in is how many zeros should be out here, or as the case may be. So here, the way you get this 10 to the minus 46 is you just count up the powers of 10. If you plug this all into your calculator, in scientific notation, you will get a number out times 10 to the minus 46. That's what this means. I'm just neglecting the prefactor and saying the important thing is 10 to the minus 46. You can get that in your head by adding up all these powers of 10. 10 to the minus 11, 10 to the minus 27, minus 31 over minus 11 squared. And if you add all those numbers up, you'll get the 10 to the minus 46. Now, why would I recommend you do that? We always want to put double checks on what we do, okay? So I know that you can take all these numbers and plug them into Wolfram Alpha or your favorite calculator or your computer, and it will spit out the answer for you. But I want you to get in the habit of double checking things so that you know if something went wrong, okay? And I want you to start getting a physical intuition about orders of magnitude. So I encourage you to, as you do these calculations, count up the powers of 10 in your head and then see if what your calculator gave you was correct, okay? If you find that there's something fishy, then you need to go back and check it. It helps you get the right answer. So in this case, we get 10 to the minus 46 newtons, all right? And that's the gravitational force. I also want to calculate the electric force. So here's what we just calculated, the force of gravity. Now we're going to calculate the force of electricity. Okay, it's the same calculation with different numbers, all right? And so here, I use the force of electricity to figure out who's got the stronger force, who wins in a fight, electricity versus gravity. And the force of electricity is 1 over 4 pi epsilon naught, just a constant to get the units right, times Q1 times Q2 over r squared times r hat. I just want the magnitude, so I'm not going to worry about the r hat. And notice that this looks so similar to the gravity, okay? So gravity and electricity have very similar forms. It's just that it's like the characters are a little bit different, right? So they both fall off like 1 over r squared, because 1 over r squared laws are very common in physics. So now we simply have to map this guy to all of our constants over here. I take the same distance, because it's got to be a fair fight. What's the electric interaction here? What's the force of electricity between these two guys? The distance is the same. The charges, I need a charge 1 and a charge 2. The magnitude of both of those charges is 1.6 times 10 to the minus 19 coulombs. Here, this constant, 1 over 4 pi epsilon naught, is 8.99 times 10 to the 9 Newton meters squared per coulomb squared. And I put that all into the equation. Now, carry the constant down, 8.99 times 10 to the 9, with the proper units in there. The charge gets squared. Q1 equals, the magnitude of Q1 equals the magnitude of Q2. So that's why I square this. 1.6 times 10 to the minus 19 coulombs, all of that squared. Here's the distance squared, 5.3 times 10 to the minus 11, all squared. And the order of magnitude of this force is 10 to the minus 7 newtons. So again, if you plug all of that into your calculator, you'll get a number, 5.37 whatever, times 10 to the minus 7 newtons. And it's the 10 to the minus 7 that we're interested in, because we just want to find out for now who's going to win in a fight, electricity versus gravity. Do you have any questions about how I set it up? Okay? All right, so now we've got a fair fight, and we can see that these guys are going to fight each other. And who would win a fight? Well, from this calculation, under these rules for the fight, electricity clearly wins. If I just take the magnitude of these forces and calculate the ratio, the force of electricity divided by the force of gravity is about 2.27 times 10 to the 39. So 39 orders of magnitude between the electric force and the gravitational force inside of a hydrogen atom. And this is why your chemistry teacher never bothered with gravity inside of a hydrogen atom. It is definitely not relevant in that problem. So electricity is much, much stronger than gravity. So let's make sure that that's actually correct. Always test things, right? So, for example, here's a hunk of wood. This is not the hydrogen atom, by the way, but I just kind of want to see, is this true in general, that the gravitational force and the electric force are so different in their orders of magnitude? So I have this piece of wood. It's got a nice little pivot point on it, so it can move in response to forces. For example, if I push it, it moves, okay? Now, this is just a bar, but it's got a mass, and the wood has mass. And in fact, these guys are gravitationally attracted to each other. See? No, okay. So one of the ways I could test that is if wow. All right, settle down, wood. Settle down. I shouldn't whack it before I do the demonstration, right? That was not fair. So people up front, watch closely. But if I put this bar close to it, okay, the force of gravity should mean that these guys are attracted to each other. And they are. It's just not enough to overcome the friction at the pivot point, okay? Now let's put some electricity in on this, all right? And if the humidity is not too high, then this demonstration will work. And if the humidity is too high, then the demonstration will fail, and we'll just have to imagine what should have happened. By the way, no rabbits were harmed in the making of this demonstration. Oh, sorry. She says she signed the proper consent forms and donated her body to science. Okay, so I've charged this rod, and now I should get a little bit of a force of electricity happening here. Can the people up front verify that I'm not touching it, and yet it's moving? By magic! No, it's physics. Could be the same thing, right? Okay, did you guys see it move? Okay, all right. The humidity is getting a little bit high for this demonstration, but there we go. All right, so in this case, I was able to get a much stronger electric interaction than a gravitational interaction. Thank you, Fluffy. Fluffy's going to take a well-earned nap. Okay, so this does seem to apply then even in our experience, in our everyday experience. I'm sure this is part of your everyday experience, running that. And so here's the thing. Let's think first about what is the difference in these magnitudes. Like we said, the force of electricity is much, much stronger than the force of gravity. Okay? So the force of electricity is much, much stronger than gravity by 39 orders of magnitude. 39 orders of magnitude. How big is 39 orders of magnitude? And that's one with 39 zeros. It's a billion times a billion times a billion times a billion times 1,000. It has a name. It's a duodecillion. I looked that up last night. I did not expect there to be an actual name to this number. I encourage you, if you haven't seen it already, I encourage you to check out powersof10.com. I'm sure one of your high school teachers showed this to you, but if not, just take like 10 minutes and get a kick out of that video. The video's from the 60s, but powers of 10 have not changed. And so the video takes you all the way from the largest structures we can measure in the universe, which are galaxy clusters, all the way down to the size of a proton. It turns out there are about 39 orders of magnitude between those scales. It's a great video, so I encourage you to check that out. So here's the question. We calculated it, okay? Electricity is 39 orders of magnitude stronger than gravity, okay? So why do we always feel the force of gravity, but we don't feel electricity as often, okay? So you are actually experiencing the force of gravity right now, right? It's the reason you're sitting in your chair and not floating off into space like an astronaut. So what's up? Why is this the case? Why do I feel the force of gravity a lot more often than I feel the force of electricity? What are your thoughts on that? Some ideas. Yes, please.
So things are, in general, more or less neutral.
Okay. All right. So one thought is that, in general, things are neutral. So like everyday objects don't get a charge on them unless we borrow Fluffy again and charge them. All right, what are some other thoughts? Yes, please.
Maybe on this scale, the scale that we're on, gravity feels a lot stronger than an electric force.
Okay, so there's a scale issue as well, which is that the force of gravity is proportional to the masses. And so for more massive objects, such as the Earth, which is massive, very massive, you may have noticed, the force of gravity is much more important. Yeah, excellent point. Any other thoughts we should? Oh, way in the back, please.
We do feel the force of electricity, don't we? I mean, that's what keeps us just like falling apart into atoms everywhere.
Okay, so he's arguing that in fact we do feel the force of electricity by evidence that I'm not a puddle of slime right now, right? You're arguing that electric interactions are actually keeping my body together. So in a sense, it's kind of like you don't really feel the air that you breathe. You're kind of made up of it. That's an excellent point. Awesome. Okay, so other things we should consider here? Yeah, please.
Well, the fact that you're sitting in your seat, you're being repelled by electric forces that keep you in place.
Okay, all right. So anything you're touching, you're actually being repelled by electric forces, right? So I'm not falling through the floor down to the center of the Earth due to gravity, right? I'm stopped by the floor, and ultimately that's an electric interaction between the floor and myself. Excellent. So we do, in fact, feel both of them. And the force of electricity on the face of it is 39 orders of magnitude stronger, okay, at least in the case that we calculated. But part of the reason that we don't necessarily experience it all the time is that there are positive charges and there are negative charges. So as you pointed out, I'm made up of positive and negative charges and some neutrons that are neutral. But the force of electricity is keeping all of those together, all right, as well as quantum mechanics. But the force of electricity is what is causing them to be attracted to each other. And so overall, I'm a neutral object. Okay, I don't have a huge net charge. Now, once it gets to be wintertime, you can net charge yourself by scraping your feet across the carpet and then touching some metal object, all right, and you'll experience the force of electricity that way. But in general, we tend to feel the force of gravity but not electricity because electricity comes in positive and negative charges, and it's such an overwhelmingly strong force that macroscopic objects don't tend to have a net charge. Whereas, as far as we know, we don't have a way to get a negative mass and balance out gravitational forces that way. Do you have any questions? Excellent discussion here. Okay, now, the electric field of a point charge is something that we talked about last time in lecture. Here's how we got the answer. We said, look, if I take two point charges and I measure the force between them, I find that the force between 2 point charges is this law. It's Coulomb's law, 1 over 4 pi epsilon naught, Q1 times Q2 over r squared times r hat, where r is the distance between the charges. Okay? We also said that the reason those two charges are exerting a force on each other is because one charge exerts an electric field that the other one feels. So if I take away one of the charges, the first charge is still exerting something in space, waiting to push or pull on any other charged particle. And that is embodied in this equation, that the force a charged particle feels is proportional to the charge times the electric field. Okay? So if there's an electric field in space, a charged particle will feel that kick. That defines the electric field. So we said if we put these equations together, that must mean that a point particle has this electric field that it's always exerting in space all the time. And when another charge comes around, it feels that. But the electric field is a real, actual physical object that's always there. Now, let's think of this, though. This guy has an electric field. Okay, it looks kind of like a dandelion. It points out in all directions if it's a positive charge. And the magnitude falls off like 1 over r squared. So it's kind of like a fuzzy dandelion that gets weaker and weaker and weaker as you go out, but it's all over space. Now, I also know that a charge will feel a force if it experiences an electric field. So here's the question. Does this guy feel its own electric field? What happens at the origin? Is this guy exerting an electric field on itself? Is it feeling its own force that way? How do we think about that? What are your thoughts? Yeah?
From the second equation, you can see that the force is proportional. I mean, there has to be a force from, a charge from another particle for it to work. Like, the electric field comes from something else, but the charge of its own, I'm not sure of the word.
Oh, okay, so let me see if this captures your idea. Okay, and then the people in the back can hear too. This equation right here says that particle 2 feels a force due to somebody else's electric field. So we have that as well. Yes, good point. What else should we consider here? Way in the back, please. Yes?
There's no distance between the origin and the node.
Okay.
Where the radius is 0 and our equation doesn't work.
Okay, all right. So this equation right here, if I look at it and I think mathematically about what happens when I go to the origin, the equation has problems, right? If you're a math major or if math is your hobby, then you've been hating this equation from the outset because it's just not defined at the origin. So as I take r to 0, then this thing blows up, and a mathematician would say it's just not defined at the origin. All right, excellent point. So we should have put a caveat on the equation from the beginning, not applicable at the origin. There's something else we should consider? There's a lot of things to consider. Yes, what are your thoughts, please? Okay, all right, so the charges, all right, so are you thinking maybe that the point, are we thinking of a point charge that has an extent to it? Or are you thinking of the point charge itself being 0? There's many ways that this stuff breaks down, right?
Yeah, well,
right.
If you consider like a proton, like the outside of a proton.
Okay, so some of these things actually have a finite extent. Like a proton isn't a point charge, really. It's just really, really, really small, 10 to the minus 15 meters in radius. And so we have to consider the fact that, okay, somewhere inside of itself it has a structure, but outside of itself it doesn't. And so, maybe it doesn't even make sense to discuss a proton unless you're outside the radius of the proton. Excellent. So, all good ideas. What happens as r goes to 0? A lot of problems, okay? You've all brought up different ideas for all the problems that happen as we go to r equals 0. So can the particle exert a force on itself? No, for all the reasons that you've articulated. One reason is that the electric field itself is undefined at the origin, okay? There's two reasons for that. One is that it blows up, okay? So 1 over r squared is not defined at the origin. The other reason is that r hat itself doesn't make any sense at the origin. This is a vector that's defined everywhere except at the origin. If I put r hat at the origin, right, which way does it point? Okay, it has a nervous breakdown because all of a sudden r hat now has to point in every direction at once, and it just can't do it. So r hat doesn't even exist at the origin. It's self-contradictory. Also, so if there were a force at the origin, which way would it point, right? It would somehow, by symmetry, it would have to point in all directions. And since force is a vector anyway, the vector sum of all directions at once is 0. So no matter how you look at it, this particle cannot be exerting a force on itself. You can pick your favorite reason for why. They're all correct, all right? But the particle doesn't exert a force on itself. Do you have any questions about that? Okay. All right. So now I want to move on to the electric field of a uniformly charged spherical shell. All that means, it's a long phrase, but uniformly charged spherical shell means that we have a ball, okay? And that there's going to be charge on the outside of the ball, uniformly distributed, and there's enough charge that it looks smooth. So consider it to be smooth, and I want to think of the case where the charges are stuck. These charges cannot move around. So it's uniformly charged, and it will remain charged the same amount on every spot of the sphere. So here's the electric field for a point particle. The electric field for a point particle is 1 over 4 pi epsilon naught q over r squared times r hat. We want to think of a sphere, but let's just think intuitively at first, okay? So let's think intuitively about the sphere, and I want to put it far away. So let's imagine zooming that picture way, way, way far away from you into the next building. What do you think the electric field should look like from that far away? Put that sphere over in the chemical engineering building. And now, what do you expect that to look like?
Should look pretty much like a point.
Yeah, it should look pretty much like a point, right? If we take that ball and we send it over into the chemical engineering building, it looks like a point, okay? And its electric field should act like a point particle. So we definitely expect that when we are observing that sphere from far enough away, that the electric field of the sphere should just look like the point particle. 1 over 4 pi epsilon naught q over r squared times r hat. All right, now, and in that case, it's pointing all different, it's pointing away. It's always pointing away from the center of the sphere. What about up close? If I get really close, pretend again that all these charges are so teeny tiny and evenly distributed that it's just a smooth distribution of charge. What does the electric field look like right here if I get right up close? Which way does it point? So let's think, if this is the x-axis, I want to put ourselves right outside the sphere on the x-axis. Which way does the electric field point there? Up close. Yeah, it's got to point away, right? So we don't know the magnitude yet because we didn't calculate it, but this sphere looks the same from any direction. Okay? And so if I had a sphere and I tried to think, well, maybe the electric field points in some different direction up close to the surface, well, which way would it point, right? This is the same as this is the same as this. So it can only point away. If it were negative charge, it would point towards. Positive charge, it points away, right? Any other thing, and I have to suddenly define a different direction on the sphere, but there is no different direction on a sphere. So it points away. So by spherical symmetry, even up close, the field, whatever form it has, is still going to have that r hat as the direction. Do you have any questions about that? Okay? Questions or complaints? All right. Always keep in mind that you can always slow me down by asking questions. So if I'm going too fast, you can nudge your neighbor, make your neighbor ask a question, and then that gives you time to think. Okay? All right. So we will calculate the whole thing when we get to chapter 16. So in chapter 16, we'll do the math full on. But here's the answer, okay, which is consistent with the physical intuition that we just came up with, which is that outside of the sphere, the electric field looks like 1 over 4 pi epsilon naught q over r squared times r hat anywhere outside the sphere. The whole place outside the sphere, even up close, it still looks like a point particle. That's a bit remarkable, but that is the case. Inside the sphere, there's going to be no net electric field. And we will we'll calculate that for real in chapter 16. So that's a bit of a spoiler. Do you have any questions about that? It's also a bit weird that once you get inside the sphere, you don't feel an electric field in there. Yet the sum of all those electric fields actually cancels out inside. Okay, the superposition principle is something that I was just kind of intuitively using without having articulated it. So let's articulate it now. The superposition principle is the following: that the total electric field is the sum from all charges. Your book has a really long explanation of that, and you should work through that as well. But in a nutshell, the total electric field is the sum from all charges. So if you're at a particular location in space, and maybe there's a charge over there exerting an electric field this way, maybe there's a charge over there exerting an electric field this way, the total that I feel is due to all of those. So here, for example, at this point in space, Q1 is a negative charge. It is exerting an electric field, E1, at that point in space, which points back towards Q1, because Q1 is negative. Q2 is exerting an electric field in this direction. Okay? Now, I didn't tell you the relative magnitudes of Q1 and Q2, but you can guess from my diagram, since E2 I have drawn as a longer vector, then Q2 must be a larger magnitude. Okay? So at this point in space, the total electric field that a test charge would feel is just the vector sum of those. Okay, so the vector sum of these is I add up those two vectors and I'll get something roughly in this direction. All right, so the other way to say the superposition principle is that fields add as vectors. They have magnitude and direction. Always remember that directional component when you add up vectors. Okay, do you have any questions about that so far? All right. Okay, so now I'd like to calculate the electric field of a dipole. Let me first define a dipole. A dipole is defined as two equal but opposite point charges, minus q and a plus q. A particular distance apart, we're going to call the distance s, all right? And the definition of the dipole moment is just q times s. And then if you want to report that as a vector, then you put the vector hat on everything. Now you've got a vector, right? But the direction goes from the minus charge to the positive charge. So the dipole moment as a vector points towards the positive, well, points this direction, from minus to positive. Let's put the origin in a reasonable spot. You always get to choose the origin when you're doing problems. So put the origin in a good spot, and we'll put the origin right smack in between the two charges. Let's orient the x-axis to be parallel to the charges and the y and z axes to be perpendicular. So that'll be our choice of origin. And I want to start calculating electric fields. Now, I'm going to pick some high symmetry points. I'm going to pick some easy spots. So we'll pick an easy spot that's along the x-axis and calculate that first. So here's our dipole. There's the origin. I'm going to pick a spot over here, the green x, and calculate the electric field at that point. So how do we do it? We'll use the superposition principle, and we'll use the equation for a point particle, that the electric field is 1 over 4 pi epsilon naught q1 over r squared times r hat. So here's our observation point, the green guy. And the distance from the origin out to here, okay, we can write that out as x, 0, 0. All right? Now, what I need to do is I need to think about the electric field here that's exerted by the positive charge, okay, which is the E plus, and the electric field exerted by the negative charge, which is the E minus. Okay, so this guy exerts this electric field. This guy exerts that electric field. The E plus is drawn as a longer vector because this positive charge is closer. So it's exerting a stronger electric field. So here, I'm talking about the components in the x direction. So I'm just calculating the x components. All right. And so there's one component that I need to consider, which is the electric field due to the positive charge right here along the x direction. That's this guy. And then the electric field in the x direction due to the negative charge. That's this guy. So we take the equation we have for the point particle and write it down. Let's first do this red spot. So the red box here corresponds to that red box. And that's the electric field here, this vector, that's exerted by the positive charge. So the electric field exerted by the positive charge, well, if I start from the point particle equation, I copy down the constants, 1 over 4 pi epsilon naught, just constants. The charge I copy down is q, okay, because that's a positive q there, so I put the q there. The distance is what we now need to figure out. We've set things up so that the distance from the origin to our observation point is called r. So the little vector r is that distance. But the total distance of the dipole, the total size of the dipole is s. So the distance between the positive charge and the origin is what? What's the distance between this guy and the origin? S over 2, right, thank you. So I have to divide that by 2, okay? So if I think of the observation point, which is a distance r from the origin, it's a distance not quite r from this positive charge, but its distance is smaller. So its distance is r minus that s over 2. Does that make sense that from here to the green x is r minus s over 2? It's that distance. So that's why I put this as the distance down in that denominator, and we'll square that. Okay? Do you have questions about how the red box is set up? Okay, so we'll move on to the blue box. The blue box here is about the field exerted by the negative charge. So the negative charge has an electric field pointing towards itself, and right here at this point, it exerts an electric field in that direction, pointing towards the negative charge. I've drawn it as smaller in magnitude than that due to the positive charge because that charge is farther away. Okay? So here is the formula for that. So we transcribe just from the point particle formula. So for the point particle, I need what is this charge I should put in. I have a minus q here. The minus sign is because this is a negative charge I'm considering. So there's a minus sign there, right? 1 over 4 pi epsilon naught is just like it was before. Now I need the distance squared, where the distance is from the x all the way over to the minus sign. Okay? And that distance from x to the origin is r, and then from the origin to the negative charge is an extra s over 2. It's a longer distance, so this is r plus s over 2. And then we'll square all of that. Do you have any questions about that setup so far? Yes, please.
If you were to change the origin so it's at one of the charges and just like adjust the equation, would it still work, or does it have to be in the middle?
Okay, so he's asking an excellent question, which is, okay, maybe you're being sneaky and you set it up at the origin because it'll work at the origin. You can always, so I set the origin to be in between, and you want to know, what if I recentered the origin and moved the origin over to sit on top of the point charge? So the answer to that is you always get to choose the coordinate system, and the answers you get, the physics you get out of it will be independent of your choice of coordinate system. Okay? So you choose the coordinate system that makes the most sense to you. And so if you did this and you carried out the physics and the math correctly, your numbers would look a little bit different in between, but at the end of the day, when you reported back to me the electric field of a dipole, we'd have to calculate the same answer, right? So our formulas might look a little different in intermediate steps, but we'll get the same physics. Okay? All right, and you always choose the one that you like, okay? Unless the problem specifically tells you where the origin goes. You choose what you like. Especially on a test, when we have a free response on a test, you set up the problem in your favorite way. As long as you explain it to us, you'll get full credit for correct reasoning. Okay, so now I need to add these two together. So you know how to add two fractions. I have to cross multiply the denominators. So altogether, this denominator is going to be r minus s over 2 squared times r plus s over 2 squared. All right? And I put an overall factor of 1 over 4 pi epsilon naught over here. We don't need to worry about that. It's in front of everything. Now I need to multiply q. Okay, I need to multiply q up here in this numerator by this denominator. So I need q times r plus s over 2, all of that squared. There'll be one term, which is r squared. That's here, qr squared. Let's do this term squared next. That's a little easier. So there'll be another term, s over 2 squared, which is s squared over 4. That's this guy, qs squared over 4. Then there's the cross term. So let's go a little slowly on that one. So I need r times s over 2, which is rs over 2. But I'll get 2 of those factors. So it's altogether r times s. All right? So r times s times this q gives me qrs. That's this guy's numerator now. This guy looks very similar, except minus q needs to be multiplied by r minus s over 2 squared. All right? So I'll have a minus q times r squared. And that's this guy. All right? Do this term next. Minus s over 2 squared is s squared over 4 times the minus q gives me minus qs squared over 4. Now I have 2 more terms to consider, r times minus s over 2. But I have 2 of those, so I get an overall minus rs. Overall minus rs times minus q, the minus signs cancel, and I get the qrs as a positive. That was long and tedious, but when you do these problems, take your time, okay? Don't rush it, because if you take your time and you're patient with it and you refer back to your diagram, and then once you get the equation, you go back and double check that everything makes sense, then you'll get the right answer as long as you're persistent and patient with it. So go back and check this when you're doing it on the homework, all right? And now we're ready to then see what cancels. So this qr squared cancels that qr squared. This qs squared over 4 cancels that qs squared over 4. And so altogether, I'm left with qrs plus qrs. That's all that survived. And so I write that down here, and the rest is the denominator. That is the dipole field, okay, the dipole electric field of a dipole along the x-axis. It's complicated looking. All right, so here's the deal. In a physics class, in this physics class, you won't be expected to memorize equations like that. That's not what we're after, okay? This is the information age. You can always look up information, right? Information is no longer power. It's knowing what to do with the information, okay? So notice that we started with a very small piece of information, just the equation of a point particle. And then we drew a very careful diagram, and we did mathematics to derive this. What I want you to learn how to do is to know what the very small input is, okay, the big idea that's the input, and then know how to construct after that. You're not responsible for that equation at the bottom. I give you equations on exams, but you do need to know how to work through problems, draw the diagrams, and very carefully go through these things. So that's a complicated equation, but let's get the physics out of it, okay? So this is a dipole electric field along the x-axis. Remember, what's above the line is what you already know. That's what we calculated on the last slide. I want to know, what does this look like at a distance? So let me put that dipole moment far away, and then what does it look like? So remember, our dipole was oriented so that we had negative charge, then positive charge, oriented along the x-axis. Let's take ourselves far along the x-axis and find out what the field looks like. So if I'm far along the x-axis, I can say that r is much, much greater than s. S is the size of the dipole, so go far enough away that that's the case. And see, one of the things you might think is that, well, it's a positive and negative charge. It's overall neutral, right? So if I put it far enough away from me, well, I just feel nothing. Maybe it's a net neutral object. But let's calculate it and find out if that's the case. So r minus s over 2 squared, when r is huge compared to s, is approximately r squared. Okay? R plus s over 2 squared, when r is huge compared to s, is also r squared. If this kind of logic makes you uncomfortable, okay, think about it in terms of money. I think that clarifies things, okay? So let's say that one friend owed you $1 billion. Let's pretend R is $1 billion, and pretend S is a penny. Which one do you care about, right? Okay? So $1 billion plus 1 penny is still approximately $1 billion. So that's what we mean when we do these things, okay? It's approximately R squared. So I put that into the equation. So now let's see what that's going to do. So this denominator, pretend that's now r squared times r squared, which is r fourth. But there was another r sitting up top, so one power cancels. And I'm altogether left with that the dipole field far away from the dipole is 1 over 4 pi epsilon naught times 2sq over r cubed. It goes like r cubed. It never goes away. That's why we did the calculation. So even infinitely far from this dipole, it's still exerting a field. And the field is going to depend on the strength of the dipole. Notice that the dipole moment made it in here, SQ. So the larger the charge, the larger the field. The larger the distance between the charges, the larger the field. It falls off like 1 over r cubed, which is a faster fall off than that of a point charge. Okay? And we're out of time, so we'll end there today, and I'll see you next week.